back to my workshop. My name is Robert. This is part 3 in the series on the Ainjest rapid threading attachment. Now in part 1 I took the attachment apart. In part 2 I'll put it all back together again. In this part I'm going to make a new bronze helical gear for the timing spindle, and then I'll fit it back on the lathe. So with that, let's get on with it. So this is the material I've got to make these gears out of. Very wasteful by the looks of it, but it's what I've got, and therefore it's going to be cheaper than buying something else. This gear is a very tight fit on my 3/8 reamer, which is a bit worrying that I'm going to end up with something that's really sloppy. But if I measure that, that comes out to 9.52, which is 0.375 inches. So that is definitely 3/8. This one is coming out at 12.7, so that's half an inch. I'm going to have to make an arbor for this. What I'm intending to do is to make an arbor that will take a half inch and a 3/8 all in one setup, and then cut the two gears together. The outside diameter of both is 1.4 inches. Now, the one thing I can be sure of is that the circular pitch of the gears, not the diametral pitch, but the circular pitch, is exactly 0.25 inches, because it engages with a 0.25 inch pitch lead screw, 4 TPI. Therefore I can do some calculations on it, and it's giving me somewhere a DP of 12.6, so it's a special. So at this point I'll deviate from the video and go through some things that I calculated after the event, after I'd cut the gear using an OD that was basically what was measured on the existing gears, and assumed that that was correct, and other things that I knew was correct. Now I'd taken some measurements on the lead screw. I'd measured the OD, which is easy. I'd measured the root diameter, but measured obviously at the helix angle. Not that that makes that much difference. We know that the lead screw pitch is 1/4 inch. That's a given, because that's what the machine is. The pitch diameter, I suspected, and from later calculations I guess I was correct, that it'd be about an inch. It's not going to be halfway between the root and the crest. It's probably going to be closer to the crest. For a standard Acme thread, the outside diameter is the pitch diameter plus the pitch over 2. That's just what the standard Acme is defined as. And that agrees with everything I've said here, that with an OD of 1.125 and a pitch of 0.25, the pitch diameter is going to be 1 inch. The root diameter, on the other hand, now that's got to be the pitch diameter minus half the pitch minus clearance, which is nominally about 10 thou each side, so take 20 thou off the diameter. Now it doesn't really matter if that's a little bit deeper. A little bit deeper is better than not deep enough, because then you've got clearance rather than no clearance. In my case, my lead screw measured at about 0.836, so there was about an extra 20 thou, so they'd done 20 thou a side. The helix angle was the next thing. Now the helix angle is not necessary for a gear which is just merely going to drive round a threading dial or the Ainjest So there's no power transfer. However, I thought I might as well, since my setup allows me to do it, I'd cut the helix angle. And the helix angle is the arctan of the pitch divided by the pitch diameter times pi. So it's how far you go along divided by how far it is round the spiral, and then take the inverse tangent, and we measure it at the pitch diameter. And this in this case turns out to be 4.55 degrees. For the pinion, this can have a maximum addendum of 0.0625, which is pitch over 4, which is back to the definitions on the lead screw. The circular pitch we know has got to be 0.25 because it's got to mesh with the lead screw, and we want the pitch diameter of the lead screw and the pitch diameter of the pinion ideally to be coincident. Now for a 16 tooth pinion, the pitch diameter is going to be 16 times 0.25 divided by pi, which is 1.273 inches. Now if you add twice the maximum addendum to the pitch diameter of this gear, you get about just under 1.4 inches, which is in fact what I measured for the gears that were on the lathe. So for this pitch diameter, if you turn that into a diametral pitch, that turns out to be about 12.6, which is what I used in the calculations for setting up the tooling to cut it on the shaper. Finish is not very good. I think this is phosphor bronze. Corner off quickly.
So this is the arbor. A little change of plan. I've put a little bush inside this bigger gear, so I've bushed the 1/2 inch hole down to 3/8, and they're both sat on a 3/8 arbor that I already had. So just saved a little bit of effort, and that's ready to grip in a collet chuck and cut the teeth on the shaper. There we go. That one's for the threading dial, that one's for the Ainjest. There's a subtle difference, but then this old one is worn. So's this one. Not so much on this side, but on this side it's badly worn. Next job on this gear is to put in a hole for the locating pin, which enables this to be timed. Now, if we look at the back of the Ainjest, the gear fits on there. It's a 16 tooth gear, and there are 15 holes around this, which enables you to put it in any one of 15 positions, which means that you should be able to get this thing to seat in the lead screw at the same time that the half nut is also firmly engaged. So the hole needs to be drilled at the right distance from the centre so that the pin that goes in the gear will go straight in the hole without any problems. Now, in order to work out what the diameter is, or the distance from the centre to the pin, what I've been doing is put a drill bit, which is a close fit, on most of the holes. Some of them are, like that one there, is a bit manked, so it won't actually even go in there, and the one below it is really sloppy. But I take a drill bit which is a nice fit, and then use the micrometer to measure across there as carefully as I can. Now, I tried to do this for all 15 positions. There were about 4 positions, 5 positions that just the pin wouldn't go in. And then measure the diameter of the central spigot and the diameter of the drill, and then basically take an average of the distance across here, subtract off the radius of the spigot and the radius of the drill. I came out with an answer of 11.11 millimeters, which when I convert it into inches is going to be 7/16 of an inch, more or less exactly, which feels right. It's going to be some sort of imperial whole measurement or fractional measurement. So I know that I need to be 7/16 from the center, or from the center of this pin to where I'm going to drill a hole. And I'm going to try and drill a hole right at the base of one of the teeth, as this one's been done, or that weaken the tooth. Or do I drill it at the base there? Decisions. So my quick and dirty technique for lining this up is just to use a square off the side of the table and just nip that down, and for what this has got to do, that's going to be accurate enough. So now I just need to indicate this pin to make sure we have the center, and then I can offset by 7/16 and I'll drill a 3mm hole initially, then I'll go in with a 3.1, something like that, 3.2 maybe. I want the pin to be a snug fit but not stupid tight. So we swoop that around. It's within 1/100 of a millimetre. That'll do. So now we'll offset the table. That's close enough. 3/10,000ths will do. And if I lock it, it moves slightly. So now we'll take the pin out. We should be in exactly the right position. Let's just check to see if it looks about right. Doesn't look too bad. Just put a dimple in there. Three millimeters. Right, I happen to have a 1/8 reamer in my collection of random stuff, so let's stick this through there and see how it behaves. painless. That's the finished gear. Hopefully that'll be good enough. Put a swathe on there. So now we come to the point where I need to align this gear into the correct hole here to time the gear with the half nut, so that when the lever is engaged and the half nut moves up, it doesn't try and rotate this, because I think that's probably what caused a lot of the wear on the previous gear. Now, you could try and do this in the lathe, but to be frightfully honest, it's very difficult to get at. It's awkward, everything gets in the way, and you have to take the end block off of the lead screw and the shafts in order to slide the on-off rod through this section just here. So I've got this clamped in a vise here. Mainly for stability. And I'm just going to try and find a point where the lead screw will actually balance in there. About like that. It's still got the block on the end, so it's a bit weighed down. Now, this is supposed to be set up with a clearance of no more than 3 thou, so I've got a piece of 2 thou shim here. I'm just going to wrap that around the lead screw, and if we make sure everything is in the right position to engage, and I can press this down find my spanner and tighten up the nut on the back. That's probably about right now. There's drag on that. But it's not loose, so that will do as 2 thou. So now I can, given that that's in its engaged position, I can now try this in a variety of positions. Actually, that one looks good. And that one appeared to be the best one. There's a little bit of play in that. So I shall get this. Put the screw in there. Get that done up. That's still got the right drag on it. That's now timed in the right position so that the lead screw and the half nut are all timed up nice and correctly. There's a little bit of play on this as well, so it's not going to wear horribly. If this is out of position, then the lead screw is going to get jammed up against it and it's going to cause a lot of premature wear. So that's this set up then. Now this is ready to go on the lathe. This is the bar that's going to mount on the bed of the lathe and is going to hold the stop block, which trips the mechanism to stop threading. It's nothing more than a piece of 3/4 by 1/4 inch flat bar with a 6mm hole in each end, countersunk to accept a countersunk bolt. These holes in the end fit on 2 points in the bed, one here at the headstock end and one here at the tailstock end. This is the stop block that I milled out of a scrap piece of steel. It's 1.5 inches by 1 inch by 3/4 inch with a T-slot milled into it to match the size of this rail. To mill the T-slot, I used a small cutter to rough out the slot and a slightly larger one to bring it to final size. These two cutters are courtesy of my friend George. Thank you very much, George. I've sharpened them, well, this one at least. This one was okay, and they worked admirably. I shall include a short clip of some of the milling now. The stop block simply slides over the end of the rail there. The rail is secured with a 6mm screw. There's a spacer to go behind here, and the spacer is thicker than these projections are wide and fits through there smoothly, so that can be fitted once the rail is mounted on the lathe. So first things first, the on-off lever has to come out. That has to be fully removed. If I'm right, it goes over there like that. And bolt there. So we get the first bolt in place. So this is the mechanism installed on the lathe. You can see how you engage it that way, and the kick-off lever operates there. those are accessible, so they needn't be too tight now, but that's very stiff. Now for the tricky bit, I think. The top support for the lead screw is preventing it going in properly, so that needs to be done after the lead screw is engaged. It's best to take this block off. I should have done that in the first place. Just remove the bearings and get this out of the way, then it can go on at the end. Okay, with all the shafts pushed home, lead screw first, then the feed shaft, and then that block goes in position. This can now be done up tight. And then the bearing assembly gets put on the end. There's no slop in that at all. It's rotating very nice and freely. Not sure what's going on there, but that doesn't feel right either. So I finally fixed it off camera. I thought I'd spare you the bad language when I realised that somebody had bent this shaft and I hadn't noticed it was bent. So it was fouling on the underside of this mechanism. But now everything works very nicely. So the last thing to do now is to just set this to a 2 thou gap. That's a 2 thou shim. Just lightly press in there. Let's get that engaged. Let's see how we're going now. That's 2. That's 3, just about goes in. That won't go in. That's 4. So it looks like a technique of just pulling on the lead screw to just deviate it ever such a little bit, just to lift this up. So there's just a fine gap between this upper support is all that's needed. So that's ready to try out. That's the normal lead screw. In the right position. Finishing touch. There it is, complete. Well, there we are, all done. The only thing that remains to do is to put the threading dial back on, which gives it its full range of capabilities. I'll cover that in the next video, when I'll also demonstrate this thing working in anger. So, until next time, thanks for watching.